Buongiorno, amici miei. I probably pronounced that wrong, but this is what Google Translate told me to say. Good day, everyone. Welcome to Data Saturday Pordenone. I am more than happy to have been invited to present my session, 5 Stages of Grief, where I talk about the internals of a hash spill. And a session like this, a conference like this, would not be possible without sponsors. So here's the slide, the sponsors. Please give them some love. If you meet them, tell them how much you appreciate that they make a session like this possible by supporting Data Saturday and by supporting the data community in Italy. My name is Hugo Cornelis, and I make SQLServerFast.com. Now, SQLServerFast.com is the website where I try to document everything people can and would want to know about execution plans, and probably some stuff people don't want to know about execution plans. Just if it's execution plan related, I want to have it at SQLServerFast.com at the execution plan reference. My second big project is the execution plan video training, which is, as the name suggests, more a training material. And this is a very extensive collection of long, in-depth videos where I teach everything I can teach about execution plans. Part of this is available for free for the community. Part of this is for sale. I personally think that the prices are really very interesting, but because I always love an audience that comes to my session, I like to give them a little extra. So from now until the end of March of this year, you can use the code Pordenone, and it is case sensitive, to get a 10% discount if you decide to buy access to the execution plan video training. I have a lot of other stuff at SQLServerFast.com as well. And the one I want to point out most of all is here at the bottom, the resources. So if you go to SQLServerFast.com and then in the menu you click Other, Presentations, Presentation Resources, you will get a page with a list of all my sessions. And one of them is, of course, this session, 5 Stages of Grief. You can click there and then you will find a download link to, in this case, only a slide deck. This is a slide only session, but for all my other sessions, it will be an archive with the slide deck and the demo code. And those are all available for free for whatever way you want to use it. For instance, just to review something or to share your new knowledge with co-workers or whatever way. I do a lot of other stuff as well, but you don't really care about that. The only thing you should care about is, of course, how do you reach me? If you have questions today during the sessions, type them in the chat and Sergio will read them to me and I will try to answer them. But if I go too fast, and that's possible because I have to cover a lot of stuff, and things are going to be dizzy in your head and you need time to process it, I can imagine that tomorrow or the day after tomorrow, when things start to click in your head, you have a question. Mail me, tweet me, I will always try to reply to your questions. Sometimes I do get a bit swamped, so if I do not reply to a question, it's not me deliberately ignoring you, it's me accidentally ignoring you. So then just send me a reminder, say, hey, I sent you a question last week, Hugo. I didn't see a reply yet, has something gone wrong? And I will be very embarrassed and tell you, sorry, it's my fault, I overlooked your mail and I will get to it. Enough about me. Let's talk about 5 stages of grief. When I first submitted this session, I thought that 5 stages of grief was a very generally well accepted theory in psychology for how people cope with grief, how people cope with loss. Turns out, when I started to do research to actually build the session, I was wrong. Yes, the theory is there. Yes, it's well known. It's not as accepted as I thought it was. There are actually lots of doubts on whether the theory is correct. There are also multiple different versions of the theory. So there I had this great idea for a session and it was ruined by reality. But never let reality get in the way of a good story. So I picked one of the most popular and most well-known versions of this theory. So according to this theory, if a person experiences a huge loss, a pain that causes suffering and grief, the grief generally goes through 5 stages. It starts with denial. People try to pretend that the problem doesn't exist. They cling to a false reality that is more preferable than the real version of the reality. You cannot continue to do that very long. So at one point, you realize that your denial was wrong. You actually have a loss to process, and then people tend to get very upset and mad at the problem. After that stage passes, they enter into a bargaining stage where they try to negotiate to alleviate the effects a bit. If that doesn't work, then they might enter the 4th stage, depression. But in the end, hopefully, and some people need help with that, and this is a bit outside of scope, but if you actually have a big loss to process and you recognize yourself in one of these stages and you find that you have trouble getting to acceptance, you might want to ask for professional help. Eventually, I hope that everyone who goes through grief will get to acceptance, to a state where they accept that they have a loss, that their world is not ideal. It still hurts. It can still hurt. It can continue to hurt your entire life, but you accept it. You embrace the situation and the consequences, and you make the best out of a good situation. That's all the psychology I'm going to do today, because that's not my job. That's not my specialization. My specialization is execution plans. I love execution plans. I love teaching about execution plans. A lot of the sessions I do are hopefully very useful, and sometimes I have these wacky presentations where I go into the internals of a specific behavior of a specific operator, and I can guarantee you right now that nothing you will learn today from me will be of any use during your day-to-day job. This is a session for geeks if you really want to understand how internally a hash match operator processes the situation of a hash spill. And the reason I talked about the 5 stages of grief first is because there is some similarity between all those stages that humans go through in the case of a loss and the stages the hash match operator goes through in the case of insufficient memory. So let's first talk a bit about the hash match. And I assume that most people will know this, so I'm going to go very fast. Just a generic overview so that we all know what we're talking about. The hash match operator, when used for join operations, goes through either 2 or 3 phases. It always starts with the build phase, where it reads all the data from the first input on top in the execution plan, which is officially called the build input. That entire build input is read into memory and stored in memory in a so-called hash table. Hash table is based on a hash value, which is computed from data in the row to give us an integer value, which determines in which bucket in the hash table the row is stored. The second phase that runs is the probe phase. That's the phase where the second input is read, and there each row is also, the data from that row is also used to compute the bucket. But now the data isn't stored, but the data we read from the probe input is compared to the data in the bucket to find matches. And then depending on the join type, inner join, outer join, semi-join, one or multiple things can happen if there is a match or if there is no match. For some join types, there's then an optional final phase where the rows in the buckets that had no matches have some specific handling. We are going to focus on the build phase today, because, well, I'm also going to talk about the probe phase, but most of the spills happens during the build phase, but it affects the probe phase too. And the final phase, I'm going to assume that that's like Microsoft generally likes to consider the final phase as part of the probe phase. So I'm not going to call that out explicitly. Now, because the build phase stores all the data from its input in memory, we like to have enough memory available. For that, in execution plans, a memory grant is used. A memory grant is the amount of memory that the execution plan needs to run. This is based on the estimated cardinality as determined by the cardinality estimator. in newer versions of SQL Server, memory grant feedback, the feature memory grant feedback may improve the memory grant, but we have a memory grant that is estimated in advance before we start running. That is the amount of memory that we get, that we ask from the operating system. We may have to wait until it's available, and then when we have that memory, we start running, and then we have to deal with that memory. The architecture of SQL Server does not allow for additional memory to be added while the query is running. So if you run out of memory, that's when we have an issue. When we have asked for 20 megabytes because we estimated that we would need 20 megabytes, and in reality we need more than 20 megabytes, that's when the infamous spill happens. Now this is all the useful information. And the last useful part is a spill is bad, it costs performance. But the not so useful part that can be very interesting is, okay, but what exactly happens during such a spill? And that's what we're going to talk about. SQL Server, when running a hash match, starts by denial. SQL Server assumes that there will be no problem with memory. So the entire process of a hash match and all the phases of the spill is called dynamic destaging. The term is on the screen right now. And the first phase of dynamic destaging is the so-called in-memory hash join, which is the join algorithm that works perfectly if you have enough memory. Let's first view in some animation how that works, so that we can then later see what happens when you spill. So in the ideal case, we allocate memory. This is the memory grant that you see in the box on the screen. That's the available memory. And SQL Server will first create a hash table. On the screen, I created just 9 buckets. A real hash table has thousands of buckets. But of course, on the screen, I want it to be visible. So I used a very small hash table with 9 buckets labeled 1 through 9. And that means that when we open the build input and we read a row, we use the hash function to compute the bucket number. The hash function results in a number between 1 and 9 in this case. And for this row, it happens to be number 4. So when we store this row of data in memory, we use a pointer to connect it to the start of bucket 4. Then when we read the next row and we again compute the hash bucket number, this goes to bucket 8. So again, the row goes somewhere in memory and is connected with a pointer to the start of bucket 8. Then if we once more get a row for bucket 4, we once more store that data in memory and connect it to the already existing row for bucket 4. Now I am going to tell you at this time that I deliberately simplified how the hash table works. The hash table has some very weird architecture and some optimizations in how it works. I talk about that in another session about the hash match operator, where I don't focus on the spill, but on the general behavior of the hash match operator. Here, the exact structure of the hash table is not relevant for my story. So I give you a simplified version of how the hash table is stored. In reality, the data is stored in a subtly different way. Anyway, once we have completed processing all the rows from the build input, we will have a lot of data in memory, and this may look a bit messy, but because SQL Server is good at following pointers, this is actually organized. I could have drawn it differently to make it look as organized as it is, but this is a sort of realistic version of how it is in memory. The data is scattered throughout, but the pointers connected, and you will see later in the animation how useful that is. Because at this point, the probe input is opened, and we do the same thing in the probe input as with the build input. We read a row, and we compute the hash value. This is 4, so now SQL Server knows it can ignore most of the data in memory. It only has to look at the data from bucket 4, which is in this case is 3 rows. So just follow some pointers to get through to get to those 3 rows. Processes all the joins depending on the join type, inner join, outer join, whatever. And then this row from the probe input has been processed. And then we read the next row from the probe input, that is bucket 7. So now we compare that row only to the rows in bucket 7, and so on. And because in reality there are thousands of buckets, most buckets will have just a few rows, and this is actually insanely fast. So this is the happy story of how a hash match operator works if you never run out of memory. However, I'm going to confess my first lie. I lied about the dynamic staging starting as an in-memory hash join. In reality, dynamic destaging starts as a hybrid hash join. But the hybrid hash join is the algorithm that starts the same as an in-memory hash join, but it has some outs. So let's return to the end of the build phase. We have read a lot of rows from the build input. We have stuffed them all in memory in this hash table. But previously, when I had this picture on the screen, I told you the build phase is done. We have no data there. We start the probe phase. What if the build phase was not done? What if we had more data coming in from the build input, but our memory is full? You can see on the picture there's not enough space anymore to store yet another row of data. Our memory is full, but we need to store all that data in memory. Well, this is the point where we get angry. Because right now we have a problem and we need to solve it, and solving that problem will cause us performance. So not only will SQL Server get angry, not only will I get angry, our users will get angry at me because my execution plan is slow. So how does this hybrid hash join work? Well, like I said, it starts as an in-memory hash join. That's why we have all this data in memory in the optimistic idea that perhaps the build input is small enough. But if we have bad luck, if the build input is larger than we were hoping, then we will eventually run out of memory and run in this situation where we have more data than we have memory. At that point, SQL Server will degrade from the in-memory hash join to the so-called grace hash join algorithm. How this works is that all of the buckets, 9 on your screen, thousands in reality, are divided into so-called partitions. And if you look to the left of the screen, I've marked them 1, 2, and 3 with Roman numerals, and I've marked them as consecutive series. This is a simplification for the visualization. What in reality happens is that the number of partitions will be determined at runtime based on expectation of how much more data we will get, and based on information already gathered around the data already in memory. SQL Server will determine the number of partitions and will set up a new hash function to come from a bucket number to a partition. So in reality, it will be, for instance, buckets 1, 4, and 7 that go to partition 1, buckets 2, 3, 6, and 9 that go to bucket 2, and the rest of the buckets go to partition 3. But for the visualization, I decided it would be simpler to do a consecutive series. So now we have 3 partitions. And at this point, SQL Server determines 1 partition will stay in memory, 2 other partitions will be swapped out to TempDB. So this is where the spill starts to use TempDB. And within TempDB, SQL Server creates so-called files. Now these files are technically in TempDB all part of a single file. If you use set statistics.io, you will see a work file line in the output. That's all the IO, or rather all the reads on all these logical files in TempDB. But in TempDB, it's logical files, and I've drawn them as separate physical files within TempDB. Now, what SQL Server does at this point is we have 3 partitions in total. 1 partition will remain in memory. That means that 2 partitions are swapped out. For each partition that is swapped out, a build file and a probe file are allocated. So we get 4 files because we need to swap out 2 partitions, and it's 2 files for each of those partitions. The SQL Server will first look at partition 2, and it will look at the first bucket in partition 2. So bucket 4 is one of the buckets that is part of an inactive partition, and SQL Server will read the first row and move it to the file in TempDB along with the bucket number so that we don't have to recompute that later. and then it will use the pointer to do the same for the next row and the next row. And once it reaches the end of the pointer, all rows in bucket 4 are now written to build file number 2. Then it does the same for bucket number 5, which happens to be empty at this time. And then for bucket 6, it also does the same. And it does this for every partition that is not active. So partition 3, also all data that was in memory is now copied to the file in tempdb. Now we can make partition 1 the active partition. That is the partition that we still have in memory, and as you see, a lot of memory space has been cleaned up. We still have this one row that we just read from the build input and that we needed to store somewhere. Let's now finally compute its partition, its bucket number. It's bucket number 4. Bucket number 4 is part of partition 2, which is inactive. So this row now immediately gets written to build file 2. Then we need to read yet another row from the build input, and that is bucket 1, part of the active partition 1. So in active partition, the row gets stored in the hash table in memory. And we keep reading data from the build input. All rows we read for partitions 2 and 3 are stored in the respective build files. All rows we read from partition 1 are stored in memory. Let's assume that by this point we get an end of input on the build input. So now we have processed the entire build input, but we don't have the entire build input in memory. We have separated it into 3 partitions. So one partition is in memory, the other 2 partitions is in 2 separate files in tempdb. Now the probe phase starts, and we read data from the probe file. But once we compute the bucket number, we again have to check, is this an active partition or an inactive partition? Bucket 4 is an inactive partition, so this data we read from the probe file cannot be processed yet. We set it aside by writing it to the probe file number 2. Then we read the next row, we compute the hash bucket. Oh, that's part of an active partition. We can normally process this as if it's a normal in-memory hash join. And we keep processing rows that way. And once we have processed all the rows from the probe input, all the rows that are part of an inactive partition have been copied to their respective files in tempdb, and all the rows that are part of the active partition have been processed. You don't see them on the screen because they have been processed, and probe rows are not saved when they are processed. Good. Now we have finalized all our read activities. The build and the probe input have both been completely read, and partition 1 has been completely processed. We can clear our memory because we're done with partition 1. And now we can start working on partition 2. So we make partition 2 the active partition. And now we need the build input from partition 2 in memory again, because that's how the hash match algorithm works. So we read a row. We remember we had this row in memory once, but we removed it from memory. But now we read it back from the build file. We check the bucket number and we store it in the correct bucket number. We do the same thing for the second row from the build file, and so on and so on. And at the end, when we have read all the rows from build file 2, we will have all the build input for partition 2 in memory, which means that we can now start reading data from probe file 2 to compare it to the rows in the correct bucket. And we can do that for each and every row from the probe in file 2 until we have processed all rows in probe 2. Then we clear out the memory again, and we repeat the process for partition 3. Store everything from build file 3 in memory, and then process all rows from probe file 3 using the hash match algorithm. So you see how much additional I/O we get from writing everything to tempdb, reading it back from tempdb, doing effectively the same algorithm multiple times, once per partition, and there is reason enough to be angry at the performance of such an event. But this is just the first stage of a spill. it can get worse. Before I go to the worse versions, I'm going to quickly explain a specific version of the grace hash join, which is called the full grace hash join. And where you notice that the grace hash join during the initial reading of the build and the probe input had one partition active and processed it immediately. A full grace hash join starts with all partitions inactive. So if SQL Server decides to do a full grace hash join, SQL Server will effectively just read the entire build input and stuff everything in TempDB. So here we get 2 files for each partition. There is no active partition. All partitions are inactive and need 2 files. So the entire build input will be stuffed in TempDB. Then the entire probe input will be stuffed in TempDB in separate files per partition. And then we do the processing for each individual partition. I found this described as a variation of the grace hash join somewhere in a research document from Microsoft. It didn't tell us whether, and if so, when SQL Server actually chooses to do a grace hash join right from the beginning of a hash match. Most of the time or all the time, I cannot know that for 100% sure. So most of the time or all the time, we use the hybrid hash join approach, where we start as an in-memory hash join and then degrade into a grace hash join if needed. But there might, in theory, be cases where SQL Server decides to do a full grace hash join from the start, which saves a bit of time if you already know that you're going to spill, because then you don't stuff data in memory first and then dump it to TempDB and then put it back in memory, but you put it in TempDB immediately. Now, like I said, a grace hash join is just the first start. Grace hash join can go recursive, and this is called the recursive hash join. So let's return to the picture we had at the end of the build phase when I discussed the grace hash join. So we had all this data for partition 1 in memory, and we have the data for partitions 2 and 3 in TempDB, and I assumed that this was the end of the build input. But what if it isn't? What if there's even more data from the build input, and this data happens to go to bucket 1, but our memory is full again? So we already had an out-of-memory condition. We stuffed partitions 2 and 3 in TempDB to free up memory and work with only partition 1, and now we're running out of memory again. SQL Server will simply use the same logic recursively. So now all the buckets of partition 1 are further subdivided into new, smaller partitions. And I've called them 1A and 1B. Of course, internally, they will not be called that. This is, again, my visualization, which helps. 1A and 1B gives me, as a human, a perfect reminder that this used to be a single partition and then was split again. And here, it's just 3 buckets, so it's hard to do a fair division. In reality, a single partition after the first grace hash join part will be hundreds or thousands of buckets, and you can easily recursively subdivide it into new partitions that still have lots of buckets. But anyway, we had 3 partitions. We now have 4 partitions because partition 1 has been subdivided into 1A and 1B. And now on the screen, you saw 2 files becoming smaller. That's, again, just a visualization. Files in TempDB don't have a set size. They grow dynamically, just like normal sequential files on your file system. They don't have a preset size. The only reason I shrunk those files on the screen is because I need some screen real estate, because SQL Server will create 2 new files for, in this case, partition 1B. SQL Server decides that 1A remains active, 1B gets inactive, and so the same process that was used for the normal grace hash join is now recursively used. All the data that belongs to partition 1B is removed from memory and copied to build file 1B. And now we have memory available again to store more data in bucket 1 in partition 1A. I clicked too fast. There is a reason this is called recursive. You can imagine if we keep reading more and more and more data from the build input, one day we will once more run out of memory, and then partition 1A will once more have to be split into 1A1 and 1A2, or however you're going to call them. So SQL Server can keep doing this over and over and over again. Every time it has to recurse, there will be more partitions that have less buckets, until finally the buckets are small enough that the entire build can be stored in the available memory. Now, this is one version of the recursive hash join. There's also a different version of the recursive hash join. So once more, we return to the end of the Grace hash join build phase. But now, at the end, there was more data for build 2. So everything for partition 1 fits in memory. Everything for partitions 2 and 3 is on disk. And here's the thing, a detail I didn't mention yet. While SQL Server stuffs data into those files in TempDB, it does keep some metadata. So at this point, when the build phase is done, an entire build 1 fits in memory, an entire build 2 and an entire build 3 are stored in TempDB. At this point, SQL Server can already predict that build 2 will not fit in memory. Now, SQL Server can, of course, say, that's a problem for later. I'm first going to do the probe phase. But the Microsoft engineers decided it would be better to handle this situation preemptively. So even though the build data for partition 2 doesn't need to be in memory yet, we already know that we will have a problem later, and we're going to fix that right now. So again, and the change is very small, but on the left of the screen, I will flip it back and forth a few times. You will see that partition 2 is now split from 2 to 2A and 2B. The same type of splitting we previously did for the active partition 1. And again, SQL Server creates extra files in TempDB. But notice how I named the new files. I have a probe 2A and a probe 2B. I have a build 2B, but I also have a build, and that's called 2AB. And again, these are my namings. These are not official SQL Server namings. The reason I call this build 2AB is because this still has the data for partitions 2A and 2B combined in a single build file. We have already split the partition into 2 new partitions, but we're not going to fix that data yet. So SQL Server knows I have a single build file that actually has data for 2 partitions. But now SQL Server first will handle the active partition. So it starts reading the probe phase, and data from the probe phase is either stored in the correct probe file, or it is processed immediately if it's part of the active partition. And this data, because we already know that we split probe file 2 into 2A and 2B, can be assigned to the correct files. So the probe files will get the correct data, but the build file is still this combined build file. And at the end of the probe phase, all the probe data that we didn't process as part of partition 1 is stored in TempDB. We're done with partition 1, and we can activate the next partition to process. And let's say that we choose to do 2A. Then we need to put data for 2A in memory. But we don't have a single file for that data for 2A. We have it combined with 2B in a single build file. SQL Server starts to read this build file, and if it's part of the now active partition 2A, it goes to memory. And the first 3 rows are all part of bucket 4 and will go to memory. But then the 4th row is part of bucket 6, and bucket 6 is not the active partition. So this is now read from the build 2AB file and then stored in the build 2B file. And SQL Server keeps working like that, so all the data for buckets 4 and 5 from the combined build file goes to memory, and all the data for bucket 6, which is now an inactive part of what was originally partition 2, goes to file build 2B. And now probe 2A can be processed, and after that SQL Server can continue with build 2B and build 3 as normal. So that's the second way a recursive hash join can work. Now, none of this is good for performance. it is good to make sure that we get the correct results, but we don't get them fast. So let's try to do some bargaining and try to gain some performance here and there. I already mentioned that during the build phase, when SQL Server puts all this data in memory, SQL Server keeps metadata. That's why we knew in the case of the second version of the recursive hash join that build file 2 was too large. But what if at the end of the build phase, it turns out that files build 2 and build 3 are both relatively small. At this point, before starting the probe phase, SQL Server will also go through all the build files it has in TempDB and check whether there are 2 or more that can be combined. Because now at this point we are sure that we have all the data for partition 2 and partition 3 in memory, in TempDB, sorry. So we know already in advance that build file 2 has 4 rows and build file 3 has 3 rows. Those fit combined into memory. So at this point, SQL Server will make a mental note that build 2 and 3 are now combined, partition 2 and 3 are now combined into a new partition. And again, I will flip it left and right a few times. If you look at the left of the screen, you will see that at this point, SQL Server combines partitions 2 and 3 into the new partition 2 and 3 combined. That means that we no longer need 2 probe files. We need just a single probe file for partition 2 and 3 combined. But again, we're not going to do anything about the build files right now. We're just going to process the probe data as we always do. But obviously, now not only the data for what was originally partition 2 goes to probe file 2 and 3 combined, but all the data for partitions 2 and 3 combined all ends up in that single probe file. And after partition 1 has been completely processed, we activate the only remaining partition 2 and 3 combined. Then we read all the data from build file 2 into memory, and then add all the data from build file 3 into memory to have effectively all the build data for these 2 partitions combined in memory, and then we can start the probe phase. So instead of having to go through the data 3 times, we actually managed to get rid of one of the partitions because the partitions were small enough that they could be combined. That's a very small gain, but it's still a gain. A different and more effective part of the bargaining phase is called dynamic role reversal. And this dynamic role reversal is a process that starts at the end of the first probe phase. So we have processed the entire build input. We have had this grace hash join. In this case, of the case of the screen, there was no recursion, but there could have been recursion. That doesn't change this phase. So we have one active build in memory. We have multiple other inactive builds in TempDB. We have one active probe already processed. The data has been produced. The probe input is gone. We have the probe input for the other partitions stored in TempDB. And normally we would now clear out partition 1 and start processing partition 2. But what if the data was distributed a bit differently? Now, when we clear out partition 1 and activate partition 2, SQL Server will again use the metadata it stored while creating those files in TempDB and say, hey, I noticed something interesting. Build file 2 is actually larger than probe file 2. Now the hash match algorithm works best if the build input is smaller. And the optimizer tries to predict which is the smaller input to get maximum benefit, but sometimes the optimizer gets it wrong. Well, we're not happy that we spilled, but we at least have one small benefit. Because we spilled, we now know for partition 2 that the optimizer got it wrong. And SQL Server will at this point say, you know what? I'm going to switch the 2 around. So the file that was used to be probe 2 and that actually comes from the probe input is now called build 2. And the data that comes from the build input is now stored in a file that we are going to use as probe 2. And the SQL Server can now read data from the build 2, which remember was originally from the probe input in memory. And then, and then start processing rows from this probe 2 one by one to do all the processing. of course, is there if there's a left join or a right anti-semi join, SQL Server has to switch between left and right because the inputs were reversed. But that's something that the hash match operator can do. And one thing I didn't put in the slide, but after deciding to reverse the roles of the probe and the build for partition 2, SQL Server will also check whether build 3 and the new build 2 actually could have been combined. And this would then be a single partition that will be processed in a single stage instead of 2 stages. So that's all the bargaining we do, and we actually do get some performance back. Now, if you are starting to get feeling a bit better about spilling, better switch off now, because we're tired. We're now ready to start going into the most depressing part of this presentation. Deliberately taking a sip of water to give everyone time to flee the room and not be subjected to this part, because you will feel really bad about the worst possible case of a hash match, which is called bailout. So to understand bailout, we have to go back to the build phase, and then specifically after we are already in a recursive hash join. So you see on your screen, partition 1 has already been split into partitions 1A and 1B. And in reality, this would take multiple iterations of the recursion, because as I said, hash tables have thousands of buckets. The number of partitions is relatively low. But if we keep doing this often enough, if we keep making the partitions smaller often enough, at one point we will have a partition that has just a single hash bucket. On the screen, because I use very low numbers of buckets, that doesn't take much time. In reality, it takes multiple iterations of the recursion. But in theory, it is possible that all the data that hashes to the same hash bucket 1 is more than fits in memory. So memory is full. We have yet another row that also needs to be stored in bucket 1. But bucket 1 is already in a partition of only bucket 1. We cannot split this any further. Buckets cannot be split. So all the data for bucket 1 is more than it fits in memory. And yet we need to store this data somewhere. If this happens with the active partition as shown on the screen, then SQL Server will at this time definitely move to a full grace hash join. So at this point, it will allocate 2 extra files, build 1A and probe 1A, stuff everything it already has in memory, which is of course for partition 1A to the build 1A file. Now memory is empty and it won't be used for some time, because now all partitions are inactive. And now SQL Server will process the rest of the build phase, stuff all the data for the build phase into these files. So now we have a full grace with all partitions in TempDB, nothing processed right now. And we will return to this picture later, because this is just one of the 2 versions of the bailout. At the end, sorry, I was too fast. We have stuffed everything from the build. Then, because it's a full grace, everything from the probe will also be stuffed in memory. It doesn't even fit on the screen anymore. It falls off at the end of the screen. But we have 8 files with all the data for the 4 partitions and all the probe data for the 4 partitions, and it's all stored in TempDB. We haven't processed anything yet. This is what happens if the in-memory partition has been reduced to just a single partition and we still don't have enough memory. Then we switch to a full grace and we stuff everything in TempDB. Here's where I should say we will return to this later. Because the second case is when there is a single bucket in a build file too large. So let's visualize that. So we have already, this is also the second case of the recursive version. We have recursed partition 2, the inactive partition 2, into smaller. We want to recurse it into smaller partitions. And in this case, we can use a partition for 2A that is only bucket 4 and a partition 2B that's bucket 5 and 6. But if you look at the data in this build file, you will see that almost all data is for bucket 4. So even though we split it as optimal as possible, we still run into the problem that bucket 4 doesn't fit in memory. Now this is the case where SQL Server will actually say, I will deal with that later. I will postpone it for now. So at this point, SQL Server will first finish partition 1. So partition 1, all probe data will be finished. The probe data for 2A and 2B will be stuffed in files in TempDB. And this is the end of basically the same picture that I showed at the end of the second version of the recursive hash join. But here, once more, because we have the metadata available, we already know that build file 2A will not fit in memory. So either for version A or version B, at this point, for version B, we have processed one partition and the rest of the partitions is there. For version A, we haven't processed anything and all the partitions are in TempDB, but in both cases, we have at least one partition where we know we cannot split this because it's a single bucket and the build file is too large. That's when bailout often has to be used. And I say often because at this point we also have the probe file in memory, and remember we have this dynamic role reversal. So if we are lucky enough that the partition that single partition that overflows has a smaller probe file, then SQL Server will reverse the roles. The probe file will become the build input that does fit in memory, and we can still use the hash match algorithm. It really gets bad if both files are larger than the available memory. So we have a partition for just a single bucket. We cannot recurse it. The build input is larger than the memory and the probe input is larger than the memory, and yet the hash join algorithm wants one of those inputs completely in memory. At this point, the hash join algorithm cannot be used anymore. That's why it's called bailout, because we bail out of the hash join algorithm into either the merge join or the nested loops algorithm. Okay, is that bad? Is that reason to be depressed? Well, let's look. So if we look at the merge join algorithm, the merge join algorithm is based on processing sorted inputs. We have two files, they are not sorted. Oh, so we need to sort them first. Yeah, so we have this build input and we need to sort it by the join key. Okay, let's sort it. Yeah, but remember, the build partition for this partition was larger than memory. So even during this sorting, we will have a spilling sort algorithm. Oh, a spilling sort, that sounds expensive. Yeah, it is. Okay, and then what do we do with the sorted results? Well, we store them to a new work file or work table in TempDB. So more IO on TempDB. Oh, and then the probe input, yeah, we have to sort that too. And remember, the probe input was also larger than available memory. So again, a spilling sort, a lot of reads from the probe input, a lot of writes to the sorted probe input. And then we can finally do this balanced line processing that the merge join is so effective at. Except that merge join is only really effective when there's a known one-to-many relationship. We don't have that. We need to use a many-to-many version of the merge, which also writes a lot of data to TempDB. So a sort that spills and writes to TempDB, another sort that spills and writes to TempDB, and then a balanced line processing that writes to TempDB. This doesn't sound like a winning strategy. Maybe we should not do the merge join. Maybe we should consider the nested loops algorithm. That's bound to be faster, right? So how does the nested loops work in the case of a bailout? Well, you start by reading one row from the build input. That's easy, it's cheap. Then we need to read the entire probe input to compare every row one by one to the build input. Yeah, that's a lot of IO, it's a large file, but okay. We read the probe input, that's good. And then we can process and produce the output for the first row from the build input. And then we go to the next row from the build input, and we have to repeat step 2 again, which was to read the entire probe input. So for each individual row from the build input, we have to read the entire probe input. And the build input was more than we had available in memory, so it's probably thousands of rows. And the probe input is more than we can fit in memory, so buffer pool, no buffer pool, all physical IOs. Okay, so the nested loops is terrible as well. Yeah. In the case of a bailout, we have to choose between an option that's terrible and an option that's terrible. Good luck making that choice. SQL Server has some logic to try to pick the one that sucks the least, but it's still going to suck. And if you run into a bailout, expect your hash match operator to run for a really long time and produce a huge amount of IO on TempDB. This is really the worst case scenario. You really hope to never run into it. Okay. But still, every loss at one point needs to be accepted. Yes, a hash match operator might spill. Yes, that will cause IO, that will make it slow. But once you accept that it can happen, once you realize this is part of life in SQL Server, hash match operators can do this, you can start doing stuff to at least alleviate the results a bit. For SQL Server, that means bit factor filtering. So I already confessed at the start of the presentation that I did one lie. There's a second lie that I propagated throughout the session that I'm going to reveal right now. Bit factor filtering is a process that's running in the background if you have a grace hash join or worse all the time. So when SQL Server was building this data during the build phase, some data was in the active partition, a lot of data was in the inactive partitions, and all the data from the inactive partitions is stored in TempDB. We told about that. There's also, that's the new part, a bitmap in memory, where for each bucket of an inactive partition, so that's buckets 4 through 9 in this example, SQL Server starts by setting the bit to 0. And when it finds a row that belongs in that bucket, and it checks that while it's putting data in the build files, it will set the bit. It may be set multiple times, but it will never go back to 0 again. So at the end, and I have used circles and crosses, in reality it's ones and zeros, but in at the end, because it's bits of course, but in the end SQL Server knows for each bucket, do we have at least one row in this bucket? And if you check the data on your screen, you will see that buckets 6 and 8 do not have any data. Those buckets are empty. This sounds silly if you look at the screen at an example with just 9 buckets, but if you realize that there's thousands, maybe millions of buckets, a lot of buckets will be empty. On screen, I had to mangle the results a bit and really use some weird data, but in reality, with a large bucket, with a large number of buckets, there will be empty buckets, and the bitmap will immediately notify them as empty. So maintaining the bitmap is overhead. I hope we get a benefit from that. Let's start the probe phase. The first row from the probe phase is, of course, the same example used every time for hash bucket 4. Now, instead of, as I told you, storing this in probe file 2 immediately, SQL Server first goes to that hash table and says, oh, wait, bucket 4, the bit is set. We have data for bucket 4, so this row might match. It may be a hash collision. We don't know that it matches. We have to check for hash collisions later, but it might match. We need the row, so this data is processed normally and stuffed into probe file 2. We still have no benefit from the bit factor. A row that can be processed immediately because it's the active transaction partition is of course immediately processed. But now the next example is the row that goes into bucket 8. And bucket 8, according to the bitmap, has no data. So now SQL Server doesn't need to store this row in probe file 3 then read it back later, and then determine that this row doesn't match anything, we already know that this row doesn't match anything, so we can process it right away. If it's an inner join, we drop the row, we don't need it anymore. If it's a right outer join, we return it to the client with some nulls for the left data, and so on. We know it's an unmatched row because bucket 8 is empty. So at the end of the probe phase, instead of having all the probe data in profiles 2 and 3, we have lost the rows that we could already process. Those rows that are crossed out, they were processed. Maybe output was produced, maybe not, I don't know. But the data was processed. And we didn't store it because we don't need to process it anymore. So we have less data in the two probe files, which means they're more compact. Which means, as you see on the screen for partition 3, we now actually can do dynamic role reversal because of the bit vector filtering, profile 3 has become smaller than it otherwise would have been. And it also means that we increase our chance to combine multiple partitions if the build files are small enough after the dynamic role reversal. So this bit vector filtering, once you accept that a Grace hash join can happen, gives you some performance back. Just as with a loss in real life, the hurt never goes away, but it degrades a bit and you learn to live with it and to make the best out of a bad situation. So those were the stages of a hash spill. I talked about the dynamic destaging algorithm that starts as a hybrid hash join, which is effectively the in-memory hash join algorithm with the option to degrade into a Grace hash join, and which can also do a recursive hash join. We talked about dynamic role reversal, which can be done after the first active partition has been processed for the rest of the partitions to check whether the build and the probe have the appropriate sizes and to switch them. We talked about bailout, and I honestly hope that none of you ever experience that in your production systems because it sounds horrible. And we talked about bit vector filtering, this small optimization in the background that reduces the pain a bit. That's all I have for now. I think we have 4 minutes left. So if there's any questions, this would be the great time for those questions. I hear no questions. I see no questions. I totally understand if this went way too fast. So if you have questions later, again, mail me or tweet me. A few more words and then I will wait for more questions. Once more, thanks to all the sponsors. I want to repeat that one more time. And once more, this is my final slide. My email, my Twitter. Do contact me if you have anything to ask about this session or about anything related to SQL Server performance, to execution plans, or to other data community stuff. I may not be able to answer your question, but I will try. Thanks for your attention, and if there are questions now, I think we still have 2 minutes left. Is there a way to detect a bailout happened afterwards during the investigation? The great question, Jason. Thanks for the question. I have to admit, if there is such a way, then I am not aware of it, but I assume, and that's me assuming and not knowing, that if you go to the extended events options and look at all the options you have there, there's a lot of great possibility with extended events to watch this kind of thing, and it wouldn't surprise me if there are extended events to go a bit deeper than just we had a spill. There is of course an extended event for we had a hash spill, but, and again, this is me assuming and not knowing, but I hope that you will find specific extended events that are more targeted towards which phases of the hash spill were used. Thanks for the question. And I see no more questions come in. So I think that this is where I give you back 1 full minute of your time. I'm so generous today. Take a 1 minute longer break than normal. Thanks all for your attention. I hope this session brought what you hoped to get from it. Please enjoy the rest of your day at Data Saturday Pordenone. And for the organizers of this event, thanks for having me deliver this session.
Thank you very much, Hugo. Great session.
Thanks. Let's see how I can stop the screen share. That was the stop screen share.